Hey there, Calc 3 folks, back here with another, well, I should really say the beginning of what might be the end of your study of calculus, depending upon where you're heading with coursework after this class. But we are here going to begin into our very last bit of material in our study of calculus here, and that would be the study of what we call vector calculus. Right? You'll notice that is the title of the last chapter here that we're looking at in the book. The study here of vector calculus, where we are going to continue looking at these calculus concepts that we've been developing since the early days of Calc 1. And we're going to be developing them in the context of what we might now say are vector fields, right? We are going to start to look at how the calculus can be used in the context of a vector field. Now, my videos over vector fields and the calculus of vector fields are going to be coming shortly, but where we do start our study here of vector calculus is by going back and formalizing an idea that we are familiar with from Calc 1 and Calc 2, and also with respect to the previous bit of material where we were looking at multiple integrations. This idea was brought into the light, and that is this idea of single integration being more formally known as an integration called linear integration. Right? And what we do want to go back and look at and make sure that we formalize here, and this is a bit that happens, what section is this in? I think this is about section 17.2 in the book, the second section into this study, where we introduce this idea of a linear integral, or what we call a line integral. And what we're going to start with is the study of line integrals of a multivariable function, z equal to f of x comma y. And we've established some of this understanding already. All right? We're going to bring back what we've established and formalize it within the context of what we formally mean by what we call a linear integral or a line integral. All right. Now, we are familiar with applying the single integral operator, right? This operator, the integration from a to b with respect to dx on both a, two variable function, y equals to f of x, right? That might exist in two-dimensional space, and on three variable functions that involve z as the dependent value, where that might depend upon two independent values of x and y. All right? We have seen the application of this operator on the case for y equals f of x developed all the way back in Calc 1. And we have seen just in the previous chapter of material, in our study of multiple integrations, the idea of applying a single integral operator to some multivariable function. Right? And what results there? If we formalize that understanding or take note of that understanding, right? We understand that when we apply this operator to the single variable function f of x, right, with just one independent variable, what this operator yields is what we call the net area trapped between the graph of y equals f of x and the x-axis over values of x in this bound from a to b. Right? That goes all the way back to our Calculus 1 understanding. That should be very, very familiar to us. Now, what we have established in the previous study of multiple integrations is that when we come back and we think about applying a multiple integral calculate, all right, careful there, the linear or the operator of integration from a to b with respect to x on the multivariable function f of x and y, that what this yields, we had noted, is what we call a net area function of y. Right? It is going to give us not just a measurement of net area, it's going to give us a function that describes net area that is expressed in terms of y. Where this function describing net area, right, describes net area trapped between the surface z equal to f of x comma y and what is going to be the xy plane in three-dimensional space at some arbitrary value of y. Right? In general, though, both cases are what we call a unique example of a more general calculation known as a linear integral of f over some curve c, right? Which is defined in general as follows. When we think of this integral operator being applied to the functions f of x or f of x comma y, as we have seen in previous material, what we are actually applying are very specific situations, some unique examples of what is a more general calculation known as the linear integral of f over some curve of c, right? Which we define down here below. By definition, right, if we assume that function f is defined over a region containing some smooth curve c, and what we just mean by a smooth curve c, we should be familiar with this idea in calculus. It's a curve that doesn't have any corners or cusps in it, right? Meaning that it has a continuous first derivative over values of it, right? Over values where it exists, right? Where if we think about C being parameterized, right, being written as a set of parametric equations in terms of what we know as the arc length parameter S, right? Not just parameterizing C in terms of any parameter, but if we consider parameterizing C in terms of the arc length parameter S, for values of S in the closed interval from A to B, then the linear integral of f over c with respect to the arc length s is given by the following calculation. Right? To begin with, it is illustrated as this linear integral or this single integral operator that's occurring across curve c and happening with respect to arc length in that description of space, right, for curve C, being applied to some function, right, where this function is defined over this curve C. And what all this means is we formally understand the single integral operator coming from our Calculus 1 understanding and the definition of the definite integral is that the single integral operator, the linear, or what we're going to come know as the linear integral operator here, when applied to a function and integrated with respect to s, arc length, is nothing more than just a limit of a Riemann summation for what is function f expressed in terms of the parameter s at some kth value in the n subintervals over which we're subdividing our curve c, times delta s, where delta s, right, is the width of these k subintervals, or these, I really should say, n subintervals of curve c, defined in terms of the arc length parameter s. Right? We do understand in general that this integral operator here does have this formal understanding. And we have developed this formal understanding of the limit of a Riemann summation as seen here back in Calc 1, right? When we formally defined this calculation, right, for the integral from a to b for f of x dx. And I do believe we formalized it back here at the beginning of multiple integration when we thought about our first iteration of integration being performed on a multivariable function with respect to x. I believe we were looking at that concept over a rectangular region, right, where we did break down this understanding. right, in terms of just the variable x, right? What we have to understand is that these two understandings are unique cases for what is formally understood as this here. The linear integral of f over c with respect to arc length s. Right? This is a very generic way to summarize these calculations seen above. Right? And all of the calculations that happen to fit this particular form, of which we're going to add to in this section. Right? If we go back and take note, the value of this, linear integral of f over c with respect to the arc length of s actually involves applying what we call the linear integral operator, right? This linear integral operator here, right, being applied to function f. Right? If we spend a moment just thinking about the value of this operator, right, as we had seen back in the case for linear and double integration, right, presented back here, if we consider just the operator, right, of either single integration or double integration being applied, there is a formal understanding to that operation. And this operator here does, in a sense, represent the length along x from a to b. Whereas when we applied the double integral operator to a multivariable function of f of x comma y, or if we just thought about the double integral operator over some two-dimensional region of space defined by R, it always just corresponded to the what we said is the area of R. Well, in general, the value of the linear integral operator does have a very generic understanding, and what it corresponds to is what we call the length of C. Right? When we integrate curve C with respect to its length, right, it corresponds to the length of C in value. Just like when we double integrate when we double integrate over a region of R in two-dimensional space, it corresponds to the area of R. We see here a single integration over a curve C with respect to arc length corresponds to the length of curve C. Whereas if C, we can go on to say, exists in n-dimensional space, and function f exists in one dimension higher than that of the space where curve C exists in, when we apply the linear integral operator to that multivariable function f, what it corresponds to is what we say is net area, right? The net area, or what we know as the hypernet area, trapped between that multivariable function f in n plus one dimensional space over curve C, which happens to exist down in n dimensional space. All right? Net area, when it is the case that C is contained in R2, right, and f would be contained in three-dimensional space, and hypernet area, when it's the case when curve C is contained in n-dimensional space where n is bigger than 2. If our curve C was to exist in three-dimensional space, or our curve C was to exist in four-dimensional space and be a hypercurve, or even higher dimensional space at a hypercurve's description, then the function f, it will exist in a space bigger than that dimension, also in its hyperspace, right? Where the net area calculation we're going to be calculating is going to be a description in hyperspace that becomes known as a hypernet area. Right? We do get this hypernet area, and maybe I should be a little cautious here, is the case of C contained in R sub n. Maybe we should say for n, right? less than or equal to 2 in value. Because this is also true for when C is contained in one-dimensional space, right? We get this net area as its calculation. So let me formalize that there, all right? If we look at an example, right, we are familiar with calculating this integral of C for FDS, right? In the case of C being contained in one-dimensional space, right, we can consider that this case given here being equal to this integration given here, right? Whereas C is contained in one-dimensional space, our function f is in one dimension larger than that, right? In the case of C contained in one dimension, we might say here, and f contained in 2 dimensions, right? We would have this scenario for the linear integral operator given by this calculation here, given by this single integral calculation that we're familiar with from Calculus 1. What is going on in this case, though, we point out specifically, is that this is a case where x, right, the values measured along the x-axis in our 2-dimensional space in our description of function f are equivalent to s, are equivalent to the measurements of length in that space, right? X, in a sense, is the arc length parameter, right? Where C contained in that one-dimensional space forms over values of that arc length parameter x in some interval from A to B and produces a net area value, right? A net area value that we're very familiar with calculating back in Calc 1. But what we really want to connect to here is that this calculation we were making back in Calc 1 for net area, right, is nothing more than this understanding here now in vector calculus, right? Or really what we would say is in, what we might say is in the calculus of space, right? Here we're looking at the calculus happening in n-dimensional space for a linear integral, right? And in this linear integral calculation, which could happen in any dimension of space, this is a specific case where C is in 1 dimension, f is in 2, and x is equal to the arc length parameter, right? This understanding then is translated as we have seen back in Calc 1 and corresponds to the net area value. Now, if we took this a little further, though, and considered the case of this linear integral operator happening, right, given by the application of it on some multivariable function in 3-dimensional space, f of x comma y, right? Again, x is going to be equal to s, the arc length parameter, and this is going to be a case where C is going to form in 2 dimensions over values of x, right? X, we might say here, still in 1-dimensional space over values of x contained in R sub 1 in this closed interval from A to B at some arbitrary value of y in 2 dimensions. Let me see here. Do I want to make a comment on F's dimensions here? Where C... At some arbitrary value y in 2 dimensions, the xy plane. Yeah, let's make note here. F, which equals the multivariable function f of x comma y, is contained in 3-dimensional space here, right? And let's point out then, this calculation here, right, produces a net area function of y. Right? Note this illustration for that case. Right? In this particular case, seen here, right, we are working with this function f that exists in 3 dimensions. That is this gray-looking surface here in this illustration that's occurring off in this 3-dimensional description of space. It's this surface occurring in 3 dimensions, right? Where what we see here for curve C is happening down here in the xy plane. It's happening in this 2-dimensional region of space, and it forms, right, over values of x that exists in 1 dimensions, right, from the value of x equal to a up to this value of x equal to b, where this value of x is equivalent to length in this space. It is, in a sense, equal to the arc length parameter. And when c is described this way, and we perform the integration over c, the linear integral of c with respect to arc length on this multivariable surface, right, the result is a net area function. A net area function of the variable y. What this results in is a description of the net area we kind of see here in this, I don't know what kind of color to call this, maybe a deep red or purple color looking here, trapped between these 2 magenta lines. One of these magenta lines being the curve C down here in the xy plane, the other magenta line being this illustration of C projected onto our surface. Trapped between these 2 magenta lines, the one in our xy plane and the one of the curve C projected onto our surface, is a region of space, an area of space. Right? That area of space, right, has a net area in value corresponding to it. Right? And that net area that corresponds to this region of space depends upon where this magenta line is occurring at relative to y, right? Here I have this magenta line for curve C occurring at this arbitrary value of y, tracked here along this y-axis. If I was to move that arbitrary location to some other position along this y-axis, this curve C would move relatively in the xy plane, still being trapped between values of x from a to b. But this net area that would form would vary. Certainly we can see if we move y closer to the front of the illustration here, that net area of space would likely shrink based upon the illustration of the surface. Whereas if I was to push the arbitrary value of y towards the back of this space, right, that net area would likely grow in its size as we consider it forming over this curve C and under this surface F. Right? That is what we are calculating when we calculate the single integral operator applied to this function of f. We do get a net area description, but what we have to understand is that it results in a function, and we saw this develop back in the beginnings of multiple integration, that it develops this function that is a function of y, this net area function that describes this region of space, right, for some arbitrary value of y. All right? So we have seen, to begin with here, this understanding, right, of a definite integral calculation, or of a linear integral calculation in the context of definite integrals back in Calc 1, right, where that calculation was presented as this, right, the single integral from a to b for f of x dx, and we have considered this calculation for the linear integral of f over c with respect to arc length also back in the beginnings of multiple integration, where we understood this gave us a net area function. A net area function for where in this case C exists in 2 dimensions, right? At some arbitrary value of y between values of x from A to B, right? Where the arc length S corresponds to the value of x, right? And the result being this net area function, right? We have seen these ideas for linear integrals before, right? But we go a little further now and we take note. We have looked at 2 very unique cases where in these cases above, right, the case seen here, the case illustrated above, this curve C was really always just a, what we might say, was a straight line curve or a straight path, right? It was a path that actually formed within the dimension or within one of the dimensions of n-dimensional space, right? What we want to generalize now into is the idea that this curve C doesn't always form such that the arc length S is equivalent to one of the dimensions of this space, right? S doesn't have to be such that it is equivalent to either x or y in value when considering this linear integral operation, right? What we are going to consider now is if curve C is contained in n-dimensional space and we have the case where arc length S is not equivalent to a dimension of R sub n. Right? Then what is going to be true is that this linear integral operation of applied to f over C with respect to the arc length of S will be equal to this integral from A to B for function f of S ds. Where if we have function f defined in terms of the arc length parameter S over some bounds of the arc length from A to B, and C is defined parametrically in terms of S, this would be our calculation. But that is usually not the case. Usually what we have is the case where C is defined parametrically in terms of T, just some arbitrary parameter, that being R bar of T in value, right? Where if we then consider this setup where C is defined parametrically by the vector valued function R bar of T contained in R sub n over values of T in the closed interval from A to B, then what is going to be true about this linear integral operation over function f, or on function f over C with respect to the arc length of S, is that it will be equivalent to this calculation in terms of T, right? In terms of just any parameter T here, right? Where if T, this parameter T is occurring from A to B become the bounds on our integration with respect to T, we do have to express our multivariable function or our function f in terms of that parameter T. And we do have to incorporate this scalar multiple given by the magnitude of R bar prime of T into our integral calculation, right? Where a little proof of the above result can be made by just noting this all happens since the value of ds dt would be equal to, now keep in mind this is, if we went to the idea that S was describing length and T was, for instance, describing a parameter like time, ds dt would correspond to speed, change in length with respect to change in time, right? The amount of distance traveled over a given time period is going to be a measurement of speed, right? So we know speed, in a sense, is also given by the magnitude of the vector valued function R bar of T's first derivative, right? Implying that if I solve this relationship for ds, multiplying dt on both sides, that this value of ds in the above understanding can be replaced with the magnitude of r bar prime of t dt. And that's what we see happening in this calculation. Right? Now, furthermore, in the case that we have f being defined by the multivariable function f of x comma y, right, representing z in our integration, and c defined by r bar of t, the vector valued function x of t, y of t, we rely on the following theorem for our calculation. Right? That theorem being presented as follows. All right? That theorem starts off by saying, well, just suppose that our multivariable function z equal to f of x comma y is continuous over this curve c, right? Where c here is defined by r bar of t. Right? Let me actually break that out here. Right? Where c is defined by this vector valued function r bar of t, given by this two-dimensional description of position x of t, y of t in the form of this vector. And we consider c forming over values of t in some interval from a to b. Then what is going to be the linear integral of f over c with respect to arc length will just be the single integral from a to b happening with respect to parameter t applied to this integrand operation. Where in this integrand operation, you will notice I do have that scalar multiple given by the magnitude of r bar prime of t, right, in that integrand. And that is being multiplied by this value here, which is just function f with its values of x equal to x of t and y equal to y of t being replaced with x of t and y of t, right? This value of x in the function being replaced with x of t, this value of y in the function being replaced with y of t, x and y being replaced with their respective descriptions in terms of t, right? These two values seen here. Where we can even go a little further is if r bar of t is described by x of t comma y of t, this two-dimensional vector, then its magnitude, the value we would actually be incorporating into this calculation here, the magnitude of its first derivative, right, will equal the square root of x prime of t quantity squared added to y prime of t quantity squared. This scalar factor would incorporate itself into the calculation seen here. Let's consider a specific example. I do think I follow this with an example. Right? Consider calculating the linear integral calculation of f over curve c with respect to arc length s for the case of the multivariable function given by this surface here. Now you will notice this surface is a circular paraboloid here. All right? This is a circular paraboloid, and we're going to calculate its linear integral over curve c with respect to the arc length of c, where c is defined by this position in two-dimensional space. It's defined by this vector valued function r bar of t equal to this parametric description of position in two dimensions. X equal to x of t is equal to t plus 1, and y equal to y of t is equal to 5t minus 1 in this description. Right? And we're going to consider calculating this linear integral operator applied to f over c with respect to arc length over c, where c is parameterized in terms of t, and t being considered in this interval, the values of the parameter being considered in the interval from 0 to 2. Right? And the value of this net area, right? Note the value of this net area trapped between F and the xy plane over curve C in two-dimensional space is illustrated as follows. What we are actually calculating is the net area seen in this illustration here. All right? Let's see here. Can I get most of this to fit in here? Let's first point out function f. This circular paraboloid is what we're looking at this portion of as this surface, this kind of orangey yellowish tinged surface here in three-dimensional space with the mesh lines, is highlighting our surface F, right? Down in the XY plane, right, forming the bottom of this three-dimensional space, we do see that curve C illustrated in magenta there, right? Where that curve C is described by, in a sense, this linear path, right? Notice this set of parametric descriptions, right? Parametric equations assembled into this vector value function's description of C with respect to parameter t in the interval from 0 to 2 describes just a linear path down in 2 dimensions. Not a linear path that happens between x from a to b for some arbitrary value of y, but a linear path that occurs in the xy plane we might say is in some oblique direction, right? It's not in a direction that is parallel to one of our dimensions of that space, right? It's occurring within two-dimensional space, right? And described by this vector valued function over this, over these values of the parameter. And what we do calculate when we calculate this is a net area. We do get a specific net area calculation, right? That net area being the net area trapped between this surface and the xy plane over curve C, illustrated in blue here. Right? What you'll notice is I did translate curve C up to the surface. This magenta line we see curving through space up here, that line actually lies on the surface described by F, and it is the projection of C up onto that surface. Where what we are calculating as a net area in this case is the net area trapped between the surface over this projection of curve C, or I maybe should say under this projection of curve C, and above curve C in the xy plane, right? This is going to be an area of space that forms here. And specifically, what we're calculating is called the net area of the space. Now, if I want to calculate the net area of that space, right, we do take note to begin with for our vector description of the curve C, right? We might point out for C, defined by r bar t equal to this, right? This vector valued function t plus 1 comma 5t minus 1. Its first derivative is simply 1 comma 5. The derivative of t plus 1 is 1, right? And the derivative of the component for 5t minus 1 is just 5. Where if I consider the magnitude then of r bar prime of t, it will just be the square root of each of these components squared, or the square root of 1 squared plus 5 squared, which is the square root of 26. And when assembled, right, which into our linear integral calculation is going to become that factor we multiply our integrand by, right? You will see this square root of 26 come in as that factor, right? And furthermore, we would note in our calculation here, since x equal to x of t is equal to t plus 1 and y equal to y of t is equal to 5t minus 1, the multivariable function f of x comma y equal to 4 plus x squared plus y squared can be reparameterized in terms of t by substituting in for x and y these understandings of t given above, where if I substitute t plus 1 in for x and 5t minus 1 in for y, I will prepare this statement here, where with the expansion of these binomials being squared, that statement can be simplified into the quadratic in terms of parameter t given by 26t squared minus 8t plus 6, where this is going to become the other factor in our integrand, the factor representing function f expressed in terms of parameter t. Right? What we have developed here in this case are the two values that are going to go into this calculation here. Right? What we might actually go along and highlight here, let's take this another step. Oop. Let's actually point out what this all equals. Well, I'll just go ahead and reform it. Is the integral for what is going to be f of t times the magnitude of r bar prime of t, all integrated with respect to t. Right? We are just going to be integrating what is now function f expressed in terms of t times the magnitude of r bar prime of t, and integrating that all right across these bounds of t from a to b. Right? We have prepared that magnitude to be the square root of 26. We have prepared that function f of t to be 26t squared minus 8t plus 26. So in our integral calculation, so in this linear integral of f over c with respect to arc length, right, it is going to be given by this integration here over the bounds of t from 0 to 2. Right? Here is our integrand. And what we can see is it is just f of t times the magnitude of r bar prime of t in this specific case. F of t is coming from our function f here being expressed in terms of t using our description of c, right, given by the vector valued function r bar of t involving parameter t, right, times this magnitude. Where this is really now just a rather fundamental calculation. This integral calculation is fundamental rules of integration. It's a single integral calculation that is happening just with respect to variable t, and what we have here is a polynomial form. Right? That root 26 can actually be a constant multiple. You can bring that out in front, and you can integrate that polynomial using our fundamental rules of polynomials, right? Root 26 will come out in front, and then 26t squared will become 26 thirds t cubed. Bump the power of t up to 3 and divide by 3. Minus 8t will become minus 4t squared. We bump that power, 1 power of t, up to 2 and divide by 2. 8 divided by 2 becomes 4. And then 6 is a constant times t to the 0 power. If we bump that t to the 0 up to t to the first and divide by 1, we will be left with plus 6t. Where this polynomial, when we evaluate it at 0, is obviously 0. But when we evaluate it at the value of 2, right, that's just going to be 26 thirds times 8 minus 4 times 4 plus 6 times 2 in value. And I do believe that simplifies, right, as follows. Right? That does become the square root of 26 times 208 thirds minus 4, which, if we make a common denominator here with the 4, becomes the square root of 26 times 196 thirds, which does not simplify any further and can be stated as 196 root 26 thirds units squared. And I throw the units squared on there to note that this does describe a net area. This is the exact net area of space seen in the illustration of this calculation. right? What we had just calculated is the area of space that's forming in this three-dimensional system, right? This three-dimensional illustration between our surface F and curve C, right? Our function F in 3 dimensions and our curve C down here in the XY plane of 2-dimensional space. There's this area forming, right? And that area forming has a size described by this calculation seen here. Right? So folks, what we first want to establish as we move forward in our study of vector calculuses is that this operator that we're familiar with, the single integral operator, is really a more generic integral operator known as a linear integral operator. Really, the big idea of what we're trying to make sure that we formalize and establish here is this idea right here, is that we have this operator that occurs, known as the linear integral operator, that illustrates integration over a curve C in n-dimensional space with respect to the length of that curve C. Right? Where that linear integral operator can apply itself to both functions in the context of f of x or f of x comma y, right? Where C can occur in some very simple descriptions of space, one-dimensional space or two-dimensional space, as we've seen set up in our study of single integration or the first iteration of double integrals, but can also be generalized to a more generic description in its calculation, where C can just be a curve in n-dimensional space happening with respect to its arc length s, and can be applied to any given function f. Right? What we're going to see happen here in the next set of notes is we are going to take function f from this calculation and not consider it f anymore, not consider it a multivariable description of some surface or hypersurface. What it's going to become is a vector field description. And what we're going to be able to also do with a linear integral operator is not only apply it to a function of f, we are going to see that it can be applied to a vector field and have some meaningful interpretation, right? And that is where the vector calculus actually begins, right? So this first section is just getting us a little bit more formalized with what we mean by a linear integral, right? What we mean by this idea here in general, that involves the application of this single integral operation or this linear integral operation or this integration that's going to occur across some curve C in n-dimensional space. All right? So folks, that is again my first bit of lecture here in our last topic here in the study of Calculus 3 material, where we are just beginning with the beginnings of vector calculus. And we are going to come back and start to see that these ideas in the context of now what are going to be vector field functions, as opposed to what we know of little f being what we think of as a scalar valued function. All right, so I will stop there. I hope you're all hanging in there. As I said, we're really close to being done this semester. With this last bit of material from the chapter, I am going to kind of jump around a little bit. I'll try to keep you in there, referenced where we are at in the chapter in terms of the material in the book. But we are not going to have to look at everything. So I will try to make sure that I hit the high points and the emphasis here in these lectures. So hopefully you are following along and watching these, and hope you're doing well out there. I know it's getting to be long. I think we're on we just finished week 4, right? of classes in this format. And I know it's not easy. It's not easy for me. I know it's not easy for a lot of my students out there, but I hope you're hanging in there, and we are almost done for this semester. So, with that said, folks, I will be back in a video that kind of continues these ideas, but in the context of what we are going to find are called vector fields. I'll see you all then.